This question involves both forces and moments. The way we can tell that is that we're no longer dealing with something that can be safely modeled as a particle. We're looking at something which is being modeled as a uniform rod. Now, whether or not the rod is uniform, if it's a rod, that means we're dealing with something which has a length that we have to take into account. The size of this object, at least in one of its dimensions, is relevant and important to the question. So we need to take that into account. We have the weight of the object itself pulling down, and the fact that this one is a uniform rod means that we can safely assume that the weight acts in the center of the object. In other words, the center of mass can be assumed to be in the center of the rod. And if they give you a question, as they often do, that says something like, explain how you've used the fact that this rod is uniform in your answer, that's how you've used it. You've made the assumption at the beginning when you made your force diagram that the center of mass acts in the center of the object. And that's what this mg force is in the middle. Mg, or capital Mg for this one, is because the rod has a mass of m, which gives a weight of m times g, m times 9.81 meters per second. And that gives you, when you multiply the kilograms by the meters per second, this is now a force. Mass times an acceleration gives a force. So this is the weight in newtons. And the distance away from the base at A is exactly little a. That's based on the fact that the uniform rod has length 2a and it's uniform. So the weight acts in the center. It also tells us about a particle of mass 2m attached to the rod at the point C. So we've got a force of 2 mg pulling down there. And they say that AC, the distance from A to C, is 1.5 a. So we've got our extra 0.5 a between this point and this point. The rod rests with its end A on rough horizontal ground. There are two key things here. It rests on the ground, so whether or not there's any friction, there's definitely going to be a normal reaction. And the normal reaction will always be normal. In other words, perpendicular to the direction of potential motion, which usually means perpendicular to the surface the thing is resting on. So we have a vertical normal reaction force on the ground. This is essentially the ground holding up one end of the rod. But it says it's a rough horizontal ground, so we need to consider friction. And in this particular case, they've helped us out a little bit with question part A, because they're explicitly asking you to consider and notice that friction acts horizontally to the right. So that's a free force straight away for your diagram. They tell you that friction acts to the right. They're just asking you to explain why. And a good way to see this is to imagine what would happen if friction wasn't there. We've got these two weights pulling down. We've got a reaction pulling straight up. But the tension force, the force at B that's pulling perpendicular to the rod, is not just pulling straight upwards. It's pulling upwards mostly, by the look of things, but also slightly to the left. And that means that if there were no force acting against it to resist that leftwards motion, then this entire object will be accelerating towards the left. Maybe not very strongly, but it would have an acceleration in that direction. So friction must be acting to resist that tendency to move in that direction. It says it's held in equilibrium, which means it is not moving. Therefore, whatever force is trying to pull it to the left, there must be a force that's counteracting that impulse to hold it where it is. There's a couple of other things I've added to my diagram. I've included this angle here. It might come in useful later on, because even though the force of T is perpendicular to the rod, which is very helpful for taking moments because we care about the perpendicular force, theta might be useful if we decide to resolve forces vertically later on. We'll know exactly how much of the tension is pulling directly upwards by using T times cos theta. Now, these other two forces, I've put some extra distances on as well. These distances are what I call projections, what mathematicians call projections. So if we project the distance A straight downwards, perpendicularly down through an angle of theta, we get A cos theta. You can even visualize the right angle triangle if you're a little rusty on this. If A is the hypotenuse and theta is the angle here, then the base that we're looking at, the base of this little right angle triangle, is the adjacent side. And the adjacent divided by the hypotenuse is cos theta, which means this has to be A times cos theta. Exactly the same sort of thing gives me the 1.5 A cos theta, which is the distance from A perpendicularly to this force. Why do we need those distances? Well, you don't necessarily. You can do this in two different ways. You can either multiply the distance to the force by the perpendicular component of the force, or you can just multiply the force by the perpendicular distance to the force. Now, in the case of the tension, I think it's much easier to notice that the distance is exactly 2a, and the tension is already perpendicular to the rod. So T times 2a, and that's all you need to calculate the anti-clockwise moment. And that's all I've got on this side, 2a times T. But when you're calculating the moment from these forces that are at a funny angle, you could either do A as the distance and then calculate the perpendicular component of each of these weight forces. In other words, work out how much of them is pulling perpendicularly into or perpendicular to that rod. Or you can calculate the perpendicular distance to the line of the force. And by the line of the force, I mean, if you were to draw a line in the same direction as that arrow going up and down, the distance from the point you're interested in to that line is the perpendicular distance to the force. And it works out exactly the same. You can either do this as A multiplied by mg cos theta, because mg is an angle of theta away from being perpendicular to the rod, or you can do the perpendicular distance A cos theta and multiply that by mg. I think this latter method is a little more efficient, and it often works out much more easily for things like ladders questions. So the moment of the mg force, the turning effect, is mg times that perpendicular distance A cos theta. And similar for the 2mg with the 1.5a cos theta. That can be simplified a bit because both of these terms on the right-hand side have got mg and cos theta as a factor. In fact, they've also got an a. All we need is 1 mg a cos theta and another 3 mg a cos theta from the 2 times 1.5. That gives a total of 4 mg a cos theta. And by dividing through by a, because it's a common factor on both sides, and dividing by 2, we can get an expression for t. And that is exactly the one they asked us to find. The nice thing about a show that question is that if you get an answer that's slightly different to the one that's requested, you can go back and you can find your error. You can look carefully for what should have been there that isn't, and perhaps reverse engineer any errors that you might have made, work out where they should have come from, and convince yourself that you're doing it the right way around the second time through. And if you get the result that's asked for, that is your verification. So as long as you've not made any jumps in your proof, as long as you've not made any leaps or guesses, if you can justify every step and you've got the right result, then you know you've done it properly. The next part of the question, part C, asks you to find the magnitude of the vertical force exerted by the ground on the rod. And this is another place where if you've forgotten to include that force, the normal reaction at A, which is quite a common one for people to miss initially, you could go back and find it now. The beauty of this is that you don't necessarily need to know R or friction to calculate what they've calculated here, the relationship between T and the 2mg and the cos theta. And that's because these two forces are a distance of 0 away from A. So the overall moment or turning effect of those two forces relative to the point A is 0. They become irrelevant when you're looking at moments from the point A. This is why it's such a useful place to take moments about. If there are forces at that point that you don't know and you don't want to find them out at this point, then they don't appear in your equation if you take moments about this point. It's a bit like resolving forces. If we resolved forces horizontally on this diagram, it would give me something that involved t. It would be t sine theta, how much of t is pointing to the left. And then on the other side of the equation, friction. Friction is equal to t sine theta. And r and mg doesn't come into it at all. None of those forces will appear because they're all perfectly vertical forces. But what we need to do for part C is actually resolve vertically. We're being asked to find out the value of r, so we need an equation that will involve r. And you could take moments, but that would lead to more complications because we don't know the value of friction. And you can't get an equation involving r without also getting an equation involving friction if all you're doing is taking moments. If you want to get an equation that involves r but doesn't involve friction, because they both are applied at the same point, you're going to have to remove one from the equation by resolving in a perpendicular direction to it. So I'm going to resolve vertically. We know that r is pulling up. A portion of t cos theta, is also pulling up. And then both of these weight forces, mg and 2mg, are pulling down. So my equation looks something like this. R and t cos theta pulling up, mg and 2mg pulling down. We don't need to consider this a cos theta and 1.5 a cos theta anymore because we're just looking at the total forces pulling in a particular direction. Now, we've been told that cos theta is 3/5. In this case, all that means is we can replace cos theta with 3/5. And since we already know that t is 2mg cos theta, when we get to replacing t with something that t is equal to, we can use 2mg times 3/5 because cos theta is 3/5. So 2mg times 3/5, that's t, multiplied by another 3/5 for the other cos theta, and then subtract all of that from 3mg. And you can throw that in a calculator to make sure you get what you should. It's always a good idea because if you made a small mistake in here, it's an easy one to fix. But we should end up with 57/25 mg, which is exactly what they asked us to find in the question.